Hello, I'm Nitin Dahad, and I'm speaking to New Wave DV at the Embedded Tech Trends Conference 2024 in the USA. And I have with me Jake Braegelmann and Jansen, who are with New Wave DV. Hello.
Hello, thanks for having us here today.
So tell me about the company and what you do.
Sure. So I'm Jake Braegelmann. I am the VP of Business Development for New Wave. My primary roles are, of course, sales and marketing, but also product alignment to our customers' needs. From a New Wave perspective, our primary focus in the market is bringing very high-performance FPGA-based computing with big network interfaces, big pipes of data basically flowing into them.
And Ryan?
Yeah, and I'm Jansen, CTO at New Wave, so I'm responsible for our technology strategy and technology roadmap and making sure that that flows into our products and product roadmaps.
Yeah, I mean, we are primarily a defense electronics company, a company that really specializes in moving, networking, sensor fusion of large data sets. So think radar, electronic warfare, EOIR, wherever you're generating large amounts of data and you need rugged computing and networking infrastructure.
EOIR, now my audience may or may not know what that is.
Sure. Basically electrical, optical, camera systems, vision systems that operate both in the visible light spectrum as well as the infrared light spectrum and actually other spectrums as well.
Okay. Now, at the conference here in Fort Lauderdale, you talked about emerging trends in embedded high-performance computing. And obviously this is for the aerospace and defense sector and what you're doing. You said a few things which maybe are contrary to what a lot of people have been saying about doing edge data processing, but there's a bit of context to that. So just tell us the gist of your presentation, but also then let's have a discussion about what are the pros and cons of edge versus cloud and how do you architect your system?
Yeah, I appreciate that question. It's a good one, and it is. There's a lot of nuance on it, not just a little nuance, but an important part about edge computing, and there's so much verbiage and language out there today about edge and pushing to the edge and AI at the edge or high performance computing at the edge. I just was stressing at the show and will again, that perspective really matters, right? To a certain decision makers, the edge is a whole platform, an F-35 or a future vertical lift airframe. I mean, that whole platform could be considered an edge computer, but when you're inside of that system and designing equipment and sensors and processors, which this show has a lot of that presence at, you got to think about that question a little bit different of what is really the edge when you're inside of the platform. And our case, our presentation, and we'll be the first to tell you, it is not always clear every time you should do this or every time you should do that. There's lots of trade-offs in this, but essentially, one of the points we were making is that sometimes in these systems, it is actually better not to push all the computing as far forward as you can into the sensor. And at a high level, the reason being there are trade-offs about doing sensor fusion, about doing dynamic resource allocation. There's only so much size, weight, and power on a system. If you can share those resources better across multi-function apertures, across multi-domain or multi-geometries where you have sensors at different places on that platform, there's benefits there, there's trade-offs there. So we just don't want it to get lost in the noise that whenever people push to the edge, it's not always all the way as far as you can.
There's an interesting point you made about if you process your data at the edge, you've discarded it and then basically it's lost for any future requirements of that data, whether it's for learning data or whether it's for other reasons that you might need it in the future.
Yeah, I mean, with a lot of the architectures we see today, you want access to all the data that you can possibly have, and you want to, it might be different types of sensors and combining that data with sensor fusion to be able to, make interesting decisions and inferences from that data. And if you're processing everything at the edge, you don't have access to that. And as we progress and move forward with AI, ML, we think there's going to be lots of algorithms being developed and coming on board that we don't even know about or think about today. And if you limit that data and process at the edge, you don't have the ability to enable those new algorithms in the future.
And is it more pertinent in defense electronics? Because I guess when you're in a sort of live, active situation, if that data's lost, you won't know any learning for the future, I guess.
Yeah, it could be lost forever. And I would also say in defense electronics, some of these platforms have to last a long period of time as well. So you don't want to do something on a platform that needs to last, 20, 30 years. You want that to be upgradable and add things as you move through.
Now, you talked about dynamic trade-offs, having to do dynamic trade-offs. So tell me, for our viewers, really, what kind of considerations do you have to make as to what goes at the edge, what needs to be pulled further back or to a central computer?
Yeah, it's a great question, and I want to stress for the viewers, when we say central computer, we're still talking on platform,
Yes,
not
correct.
necessarily back in a cloud, but on platform. The trade-offs are
That's because in an F-35, you can't really send something back for a decision to be made on. Yeah.
Exactly. So when we say send something back, we're really talking from the very edge, like an actual sensor, to more of a sensor fusion processor. And the important thing to at least consider, because I can't say that there's always one way to do it, but the important thing to at least consider is you only have so much size, weight, power, and you only have so much computing resources. If you can allocate those resources to like a centralized, fusion processor, you can dynamically trade off different data sources, different data modes, maybe different missions, different functions, where if you push everything as far as you can to the edge, in some respects, your trade-offs are not limited because you don't have the ability to at one moment operate, with maybe an emphasis on this domain and then in a different mode on another domain. It's kind of already allocated.
Yeah. One of the things you talked about was, I think you said chiplet infrastructure will dramatically change what we can do in these sort of compute environments, rugged compute environments. Tell us a little bit. I mean, we're seeing chiplets in obviously automotive and various other areas. In your world, where is that making an impact?
Yeah, I would say, in this kind of architecture that we're proposing, where you're pulling data in from the edge to the central processing area, you need really swap efficient entities at the edge where the sensors are. And really, what we're saying is, if you're able to digitize as much data as you can right at the edge, and then move that data back to the central processing area, that's what we're proposing that you could do, and chiplets really enable this, because now you're able to do things like put A to D and D to A converters in the same chip, where you have some limited DSP processing, and then also add your integrated photonics into that chip, so that significantly reduces area, significantly reduces power, and improves the bandwidth so that you can move those large amounts of data into that central processing.
Yeah, you did talk about having to have bigger pipes then as a result.
Yeah, exactly.
Yeah, Ryan kind of touched on it there, and he's definitely the guy to speak about the chiplets, but from a kind of where you want to be, in an ideal state, at least in some instances, if you could do all your digitization, so maybe of spectrum or a video, as far to the edge as possible, but then move all the data optically to that centralized processor, that's not always going to be possible, but certainly that gives you the most data and the most dynamic ability to change what you're doing with that data at any given time.
All right. Now, tell us a little bit about some of the examples of, obviously, it's defense, so you can't talk about names, but some of the things you're doing and what are the technologies, because maybe our viewers will be interested in.
Sure. So certainly we aren't going to necessarily talk about specific platforms, but in general, wherever you're generating lots of data. So typically we're talking mission equipment in our industry's parlance, and that would be things like radar, it would be things like big camera systems, electronic warfare, signals intelligence, where you're taking large chunks of the RF spectrum, digitizing that spectrum. That's really the domains we're talking about here. Communications also. And what our focus is not on the analog side. There are a lot of great companies out there that do wonderful things on building radios or building camera systems. We're really talking about the heterogeneous processing elements, so things like AI, FPGA fabrics, embedded ARM cores, those type of technologies, and then big data pipes to get all this around in a rugged, swap-constrained environment.
And so you've been going for what, 10 years?
Yeah, we're at 11 years actually
11 years,
now.
yeah.
And this has been and continues to be our primary focus in this space, in this rugged computing environment where you have lots of sensor data moving around.
And tell me now a little bit about the context, because we heard a lot of presentations at this conference. What were the things that sort of piqued your interest in the areas you're doing?
I think we both probably have something to say on that, but certainly New Wave participates in an ecosystem here, right?
Yes.
We're at a conference all about standards-based open systems, having a very dynamic market where you have people that build GPU cards, CPU cards, backplanes, power supplies, FPGA cards. New Wave exists in this ecosystem and is excited about existing in this ecosystem. So things like very high bandwidth data transfer, backplanes to support interconnectivity between all these different type of processing elements, shared protocols so that we aren't basically so that we're being as efficient as possible for these systems moving data around.
Anything that you speak to your interest as the CTO, you must find some things that you want to take away.
Yeah, I mean, I think it's really interesting taking, all these things that are happening in the commercial data center and trying to make those in a rugged form factor that can be used, in this mil-aero environment. And especially interesting is trying to interconnect all these different types of processing and entities in a heterogeneous fashion so that you can really take the best tool for the job and be as power efficient as possible when you're trying to solve these problems.
I think connected to you, I think one of the key things were the things like the direct RF, the high bandwidth connectivity protocols and all that. I think those probably are related to a lot of what you are doing as well then.
Yeah, for sure. And all the interconnects, being able to connect all these things together in a way that they can work together easily and understanding, the new protocols that are coming out, Rocky V2, CXL, the Universal Chip Interconnect Express as well is really exciting and really enabling this chiplet heterogeneous architecture.
I think you come from sort of various backgrounds, but is there anything specific in the rugged mil-aero space that you have to do differently? Is it related to standards and reliability, or is it sort of mission critical stuff? With stuff you're doing on data processing, is there something different to the commercial world?
I think there is now, kind of all of the above to some extent, but some specifics. Ryan hinted that we aren't trying to reinvent the CPU or reinvent the FPGA, but the challenges in our environment around size, weight, and power are extreme. I mean, sometimes beyond extreme, really, what you have to operate from an environmental perspective. And then layered on top of that is, it doesn't just have to operate in that environment for 6 months or 18 months. It's got to operate in that environment for generally 10 plus years.
Yes.
Yeah, I would say too, you're trying to find, you have to use, we're looking at commercial silicon, and some of that is, that doesn't withstand the temperatures that we need to be able to go across, and it might not have the long life availability that it needs. So we have to work with our suppliers and vendors to make sure we can get parts that meet those temperature requirements, that meet those lifetime requirements, and then put that through a whole series of qualifications as well. So
there's one thing I was wondering, in the automotive electronics world, the big thing that automakers are talking about are software-defined vehicles, over-the-air updates. How does that translate to the mil-aero environment, where you've got these FPGAs, you've got these big sort of data pipes? Is there potential to do those, or is there too much at stake to be able to do over-the-air updates because of the potential for hacking?
Yeah, I think over-the-air updates is probably a no, to be honest. However, I want to stress, and if you go and look at any of our Department of Defense leadership, they're saying things that at least would be in line with what you just said, which is it can't take 9 months, 12 months, 18 months to do software releases, firmware releases. It's got to be on the order of days, and really that's a big change. And so there is a lot of that drive, even if it's not going to happen over the air.
Right, and that's a hard problem to solve too, because you have, year-long qualification cycles sometimes for some of these pieces of equipment, but then you want to be able to, get the latest training data in for your AI ML algorithm, and you want to make sure that's safe and is going to do its job as well. So the ability to quickly do updates, on a day-to-day or week-to-week basis is important, and that's a big driving force moving forward.
So thank you very much for that. Any sort of closing sort of comment you want to make about what you've seen this week, or what you wanted to make as a point on the stuff you're doing?
It's just an exciting time. The open systems drive, kind of coupled with, or at the same time concurrently as the big innovations in silicon, optics, chiplets, is going to drive a whole new period of innovation in the DoD, mil, defense, electronics networks, and it's an exciting time.
All right. Well, good. Well, Ryan and Jake, thank you very much.
Yeah, thank you for having us.
Thanks.